So we're starting the recording again. Do Jesus or Pablo, do you have anything to add before I?
No, thanks. Just we just have your presentation to close the session of IMG. I mean, I don't know if Pablo, I don't know if he's already left.
Yeah, I'm here. Go on, please. Nothing to add. Thank you.
Okay. Also, here by my side, I have my colleague Bo Schenkman, that's also a co-author of the work that I will be presenting. So, so I will be sharing my screen and start the presentation. And I ask that, as everyone else, do you see my screen?
We see it now in full screen. Yes.
Yes. Okay, excellent. So this is a work that was done as a master's thesis project of a student from Uppsala University called Walter Godin, and the supervisors were Bo Schenkman and myself. Bo Schenkman is also affiliated with the Royal Institute of Technology and also with RISE, as I am too. The background to this project, and also similar to a project I presented at the last VQEG meeting, is about the deaf and hard of hearing persons. And in that context, they have difficulty understanding speech in noisy situation, or if there are many people speaking. So we had a project. This project has actually ended during this year, where we were looking at speech to text in augmented reality. And the idea was to create an AR aid that presents text in real time to deaf or people with hearing deficits. And this was conducted in collaboration with the Swedish Association of Hard of Hearing People, and financed by the Swedish Innovation Agency, Vinnova. So, but here we are not going to focus on augmented reality, but instead we are looking at the virtual reality as a part of this project. We studied text presentation, and to have more control of the environment, we did one of the studies in virtual reality. So this will not be about augmented reality, but rather in virtual reality. And what we were looking at was legibility and perception by the user, and also as the equipment we had contained also an eye tracker. We did eye tracking measurement for reading. We had reading speeds as an approximation of legibility. And text legibility is how clearly a reader can differentiate individual letters and word, as a contrast to readability, which is the ease with which a reader can understand the written text. But here we have concentrated on legibility. And this is not a new topic. Many aspects of this have already been studied for printed material, also for regular display. So as text size, line length, spacing, and some of this may also be applicable to digital media. So the research question. So the effects of the text size, position of field of view, and the presentation style in VR. I'm sorry, may I ask someone to mute their mic because there are some background noise. So text presentation style in VR on text legibility, the user experience, and perception. And the measures were eye metrics and perceptual and behavioral measures. And the text parameters that we looked at was text size, small, medium, and large, number of lines, 1, 2, and 3 lines, and the position of the text, above or below. I will be given more exact what we mean by this as the presentation goes on. And also we had we call a middle layer, none, Gaussian blur, or solid. We'll also explain this later. So the experimental setup and design, as this was done during one of the worst pandemic times in Sweden last year, we had to do a lot of adjustment from the original plan. So instead of doing this in the lab at RISE, it was done in a fraternity room at Uppsala University, which was large and with a big volume, so we could keep distances, and also there was a lot of air in the room with good ventilation and so on. And also another adjustment to the test plan from the beginning was, of course, that we should have had people with hearing deficit, that this was not really possible as the situation were. So it has been done with hearing test persons living in the vicinity in Uppsala, which is a smaller city than Stockholm, so people could come to the lab, or this lab, without more or less using public transportation. And of course there were face mask, hand washing, cleaning, distance, and so on, and very strict rules were applied for this. We used an HTC Vive VR headset, which contained a Tobii eye tracker, which was used for this experiment. We had 3 different sessions, A, B, and C, and half of the person would start with A and the other half with B. And for the session A, we had a search task, and for session B, there were a reading task and followed by rating. And for session C, which was done after A and B, for every test person, the test person could select their own preferred settings. We had 20 participants, 12 males and 8 females. They were in the age range of 21 to 59 with a, no, I don't remember the mean exactly, but it was towards the lower to younger age. So because there were a lot of students involved. Session A, as I said, is a search task, which should count the odd letters, and you would be presented with a text string, and you should identify the number of N in the string of M, which were randomly presented. There could be 1, 2, 3, and there were also decoys into this. So when you have counted the number of N, you should press a button and give a verbal response. The independent variables, we had 60 different conditions. Text size was one of them. We have 3 different levels. We have 7 DMM, and DMM is distance independent millimeters, which is the height of a character 1 millimeter at the distance of 1 meter. So it doesn't really have a dimension, but so it's a little bit like the viewing angle, so to speak. We had 4 middle layers, none, solid, light, and strong blur. We had 5 different backgrounds: argile, bricks, ground, stripes, and stones, looking like the pictures here. And the dependent variables were duration to complete, number of hole fixation, average fixation duration, average amplitude of saccades. And what is the middle layer though? To the left here you will see no middle layer, so the text is just presented on the background. But if you have a middle layer, which will be presented here on to the right, there will be something in the background covering the background, like a middle layer. There could be different levels on this. And the blur one was the first one, and this was the second one was the solid one. A little bit of the results and looking at the duration compared to the size of the text, and on the y-axis we have different comparisons between different text sizes. So on top of the y-axis we have a comparison between 7 dmm and 21 dmm, the smallest and the largest text size, and then the smallest and the middle size, and then we have the middle size to the smallest. And on the x-axis we have the estimated mean difference duration in milliseconds. And if the this confidence interval is containing the 0, there is not a significant difference. Otherwise, it is a significant difference on less than 0.01. So the estimated difference of the different text sizes, you can see 95% family confidence intervals. If the interval contains a 0, it's not significant. There was no significant difference between small and medium text sizes, and the large text sizes took on an average that was 1 second longer than the small and medium-sized text, as you can see by the graph. Duration for the different middle layer. Here is also this type of comparison graphs where we have the comparison between two conditions on the y-axis and the difference in mean duration on the x-axis. So there were no significant difference between blur and no middle layer. There were significant difference between solid and the other middle layer. That reduces the between average of half a second to 1 second. So in summary, for session A, we had significant difference for all variables. Text size, large text took the longest time. Large text required shorter but more fixation. For the middle layer, only solid middle layer had a significant effect. The background ground was more legible, fewer and longer saccades. The stone was the worst, more and shorter saccades. You can also see on the busyness of these backgrounds which one would probably be the hardest one. Session B, you have to watch a mute video. There is a man that talks about Swedish furniture, a Swedish furniture company. This was produced by the Swedish Public Employment Services. It's 20 seconds long and text was presented. It's not shown here in the image, as you can see. The variables, we independent variables for 54 conditions. We had 3 levels of text sizes, 11, 16, and 21 DMM, with 3 different Middle layer, none, blur, and solid black. And 3 different number of lines, 1, 2, and 3. And also different positions of this text, above or below the speaker. Dependent variables were a score given to 3 category scales, number of Hall fixations, average fixation of duration, average amplitude of the saccades. The category scales were 5-point scales. One was how legible was the text, from 1 was illegible to 5 very legible. 2, how comfortable was the text, from very uncomfortable to very comfortable. And 3, was the text in the way of the presentation. 1 was completely and 5 not at all. Here are some results from the legibility of the position and middle layer. And here on the left y-axis we have the comparisons between different conditions, blur and solid, middle layer and our different middle layer. And also to the right there is a grouping that whether the text was presented below or above the person talking. And on the x-axis we have the mean difference of legibility. And we can see that the above had a higher legibility. It improves about 0.5 points on the 5-point scale. Below then had worse legibility. Okay, improves almost 1.5. Maybe that's not correct. This should be then worsen with 1.5. Middle layer have larger effect on already bad legibility. Looking at the comfort, this is even more complex graph where we had different comparison between text sizes on the y-axis to the left, and also a different number of lines to the right. So here we have for one line you have 16 dmm with 21 dmm, and for 2 lines and for 3 lines, and then you have the mean difference of comfort. And as before, if this confidence interval contains 0, it's not significant. You can see there is a borderline significance here in the middle. So large text and 1 line was bad, and combine large text and 1 line make a bad combination. Large and 1 line was about 0.7 worse. Okay, and to summarize, we had for text side, largest text was less comfortable, and also abstraction increased with text size. Smallest text had longer but fewer fixations. For the middle layer, improved comfort and legibility, both blur and solid reduced fixation duration. Solid was in the way of the presentation. Number of lines, 1 line worse legibility and comfort, 3 line in the way of the presentation. Position of the text, above got better scores of legibility, and because it was detached from the video. This may actually depend very much on the content, of course. Section C, last session for all test person, it was to utilize the knowledge and preference from the previous session. It was the same video as in session B. The task was to set the most preferred settings for the 4 variables. Same variables as in session B, so you had text size, middle layer, number of line, and position. And to summarize the results there, here we got larger variation because I guess it was a free task. Text sizes was chosen between 7 and 21 DMA. That was the whole range. The average was about 14. Middle layer, there were 4 choosing none, 10 choosing blur, and 6 choosing solid black. Number of lines was 6 choosing 1, 12 choosing 2, and 2 choosing 3. And the positions was almost even when it comes to above and below. So design recommendations. So not text size, not too big or not too small. About 14 dmm distance in independent millimeters. Middle layer, Gaussian if background should be visible, and solid if legibility prioritized. 2 lines of text, that was I think very clear, and position, that's more I mean debatable. I mean below is probably preferred, but the data is more or less inconclusive, I would say, in this, because the session C is a little bit against what we got in session B. So, but I think it's very much what they said. It depends on the content on the video. And that's it. Thank you for listening. So let me see if I can get out of the presentation mode. I don't see anyone else at the moment.
Thank you, Shell, for this presentation. Margaret has a question, please.
Not a question, just I want to thank you, Shell, for sharing these results. That's very interesting.
Okay, thank you, Margaret.
More questions for Shell?
I have a general question, so it's not strictly directly with that, but a bit. I have the, I have the impression that we have a lot of so we have a lot of debate and discuss here about how we evaluate the quality of visual experiences, including immersive and not, and particularly also about immersive ones. And something that we don't test too much, and maybe it's useful for immersive, is testing about test legibility, not particularly in this context, but in general, in the sense that when people test our eyes, they test if we are able to retest some text at some distance. So somehow, if the system impairs our vision, it should probably impair how we read text in a way which is, more. So if we think about not at the high level communication or perceptual or experiencing, but more about the psychophysiological way. So the most low level thing. Maybe text readability is something that could be interesting to study, not only in this context, but in general in the context of evaluating visual systems. And it's I know it's an idea that I've been thinking about, but not too much. And since you have experience in doing specifically experiments about test legibility, do you have an opinion about that, or how's your feeling that this could be extrapolated or explored to other kind of evaluation. I don't know if I explained myself.
I mean, I can comment, at least I think it is relevant, and I also think that and Andrew Watson did a work on this regarding to task-based evaluation of video quality, where they where you actually through this standard observer model you put out different type of characters. So the systems were basically evaluated on its performance to render characters in a good way, and that could be more, let's say, relevant when let's say evaluating a system for its task performance quality rather than our normal let's say video quality evaluation. I don't know if Bo has a comment on this. For you have done also studies on legibility on displays before.
Yeah, thanks. Sorry, I'm not sure I really understood the full question, but there's lots of tests have been done on difficult for people to read and understand text, both what concerns the fonts, how they are made, but also the contents, and how it affects, for example, people who have reading disabilities. So there's a whole basis or documentation or literature on these aspects, on how text should be used, and the people who make, for example, books or journal articles, the editors, they are quite aware of the difficulties. Was this a reply to your question? I'm not sure.
I'm not completely sure I understood the question either, but but if but maybe you can follow up, Pablo.
Yeah. So my I don't have a clear question, and probably that's the basic problem. I somehow have the feeling that all the experience that there are in evaluating legibility of text might help us in the technical evaluation of systems which are where we evaluate the visual quality that are provided by our systems. And it's a kind of evaluation which is typically not done, mostly because if in the traditional, let's say, television or video, entertaining video content, we are not normally reading things on television, but watching movies, and then the relevant content is not particularly text. But since reading task is a very basic standardized task, it's actually the task that the optometrist use to evaluate the performance of our visual system. I think that it might be useful to incorporate this kind of tasks in the global pipeline of evaluating our video compression or virtual reality or whatever systems. I mean, in general, not so maybe we could extract some lessons from this legibility test that we can apply to the broader evaluation of compression technology or display technology or representation technology of visuals in general. That was, but I don't have a specific, more narrowed out question, because I don't really know exactly if there's a specific lesson that we could extract to extrapolate to other evaluations. It was
yeah, if I understand you correctly, I think it's you have a point, because reading both legibility and readability, it appeals to higher functions in our mind, how we processes this kind of information. So it could be worthwhile to look on these aspects also. That's how I see it.
Yeah, I kind of agree. I also think that it is it also very challenging for the system to render these characters, because they normally also contain a lot of high frequencies, and so I guess if the legibility goes down, I mean, if you can measure that also objectively, we probably get a hint on the actual performance of the system. So you can put like the system aspect, and if you can relate that to all the bulk of research that have done to human legibility, then I think one might have kind of possibly a good indicator, I would say. So yeah, that could be an interesting idea to explore.
Thank you. Anyway, very interesting presentation and very interesting work. Thank you both.
Thank you, Pablo.
Thank you.
Alex has a question also. Please, Alex.
Yeah, sorry, I was briefly distracted, so sorry to ask so late. I'm not really sure. Maybe you guys know whether that's actually applicable. In audio perception, right? There are effects of temporal unmasking across multiple bands, right? If there's some kind of co-modulation happening, I was wondering whether any such effects could help in the context of complex backgrounds, right? To have some very slow kind of modulation of the text or so. I have no clue. I checked a little bit on Scholar, so whether I could find some literature about this. But of course, it's not some thing that you would easily normally have in real life, right? Unless you have something like AR, like you're looking at right now. Maybe it's a complete rubbish suggestion, right? And it just doesn't work at all. I don't know. And obviously, a quick variation of the text would be really annoying. But I don't know. I was just thinking about it and wanted to suggest it. Thank you.
I'm not completely sure I understand the question, but I think is it you can in speech by having a slow modulation of the background noise or sound make the signal stronger to capture?
No, it's more that if you have some parts of the spectrum which are masked, so like narrowband noise or something, and then you modulate this, and you actually have some non-masked component that is basically co-modulated, then you are actually unmasking the masked component as well, right? And so it was just an how should I say, allegory that I was thinking of, some analogy that I was thinking of. I was more thinking about this temporal thing per se. I mean, could some slight temporal modulation that you temporarily modulate the amplitude of the brightness of the text, so to speak, in front of that background, make it more salient so that you can read it better. That was just my thought. I mean, maybe it's complete rubbish and there's probably literature about this, but at first sight I couldn't find anything, and I was just wanting to throw this here in the garden of experts of visual perception, thinking that maybe you know about whether there are such effects that occur.
I'm not sure, but I think you refer to what's called binaural masking level difference, where you have, for example, noise in both ears, and then you have a signal in one ear, then you can perceive it easier by BMLD.
No, I'm actually referring to the co-modulation masking release. It's completely different effect, right? It was just, so we should not be distracted by me mentioning this effect, right? It's more that I was thinking whether some temporal modulation could possibly assist in this context. Probably somebody has done some basic research ages ago about this, right? So I'm pretty sure this is not a very new idea. But I was just thinking, because I see all those things that you have looked at, but I think if I understood it correctly, but I was also outside for a moment, that you did not use somehow, a slight kind of variation of the text amplitude because I think one problem really is the saliency in front of the background, right? As far as I could assume. Never mind.
Yeah.
I mean, we maybe also have this offline. It was just a thought that I wanted to bring up.
Yeah, I mean, just for the technical aspect of the experiment, there were no the middle layer were fixed in time. It was like either it was a blurred one, it was a solid one, or there were no middle layer. So there were no temporal variation. But of course, that could have been something that could be interesting to explore, if that could in some way or improve or worse the situation of reading, so so to speak. But there are of course a lot of work done on visual masking that that may be go in line with what you are thinking about, but I cannot really think of anything at the moment. But at least the mid layer were fixed in our experiment.
Yeah, I understood this. My question was more, would it be an idea to consider something where that is not the case, right? Just to, you know, and like another option for making this better readable, right? Because you are summarizing some effects that may improve legibility, right? And I was just, but I mean, as I said, let's not lengthen this. I mean, you know, I will look more into the literature where there's any indication whether this idea could work. Thank you.
Yes, thank you. Okay, any more questions or? So I guess in that case, our presentation has ended, and we can continue with the rest of the program. I hand it back to you, Jesus and Pablo.
Yeah. In fact, the IMG session also is finished with this presentation. Pablo, you want to add something?
No, that we hand over back to you, Shell, to follow up with the program.
Okay, and then I will hand it over to Margaret to continue with the norm session.
Thank you.
I will stop sharing
you.
as well.
So Yanis was going to lead the discussions following, but instead he is with his wife at the hospital who's giving birth. So congratulations go out to him. And we're going to be delving into more detail on the standard metadata for video streams. And before we delve into that, I'd like to do a quick poll by the chat of who's interested but was not present for Tuesday when Yanis went over the document, because I don't want to repeat what he said if everyone here was there at that point. If you could just say I wasn't there on the chat, I'd appreciate it.
Could I interject quickly? I think
Sure.
you might have skipped over me. I think my
Oh,
talk,
no.
we
Oh my
rescheduled my
goodness,
talk for
you're right.
today.
I'm
Just to
sorry,
make sure
I
that
did
I'm not
forget about your talk.
seeing ghosts
Nope,
right
you're
now.
right. You go first.
All
Sorry.
right.
So redirecting. Please, Franz.
That's perfectly
you're right.
fine. I mean, this was completely out of the order anyway, right? You only rescheduled this on Tuesday, so that's absolutely fine by me. But I'm not mistaken here, right?
No, you are absolutely correct. This is the expected order.
All right. Okay, so
Please.
then in that case, I can just share my screen. Do I need rights for this, or is this? Oh no, this should work out of the box. You should be able to see my screen, hopefully.
Yes.
All right, thank you very much. Okay, so then thanks for switching gears there right in the middle of your segment, Margaret. And thank you everyone for attending. This is essentially a continuation of, and this was originally scheduled on Tuesday. It would have fit well there, but I was also feeling a little under the weather, so I was happy to reschedule for today. So I would like to talk about the Convert 150K data set. and objective metrics that we evaluated on it, as well as general sort of understandings and interesting findings we had as we were creating this this data set. This is sort of, if you remember Margaret's presentation on Tuesday as well, she touched on a variety of different video data sets. One of them was CONVID-1K, which is essentially the small brother of this data set that I'll be presenting today, and sort of a continuation of the research efforts there, and a central part of my dissertation that I recently handed in. All right, so I'll briefly introduce the data set. If you have any elaborating questions, we can go over some more clarifying details about the data set itself later on. Let me see why. Now it goes ahead. All right. So CONVID-150K is basically the starting point for CONVID-150K was YFCC 100 million, this large image and video repository by Yahoo and Flickr, which contains user-generated content ranging from, I think it's around 2002 to 2016 at the time that we accessed it. And in total, it contains around 800,000 videos, from which we sampled in a way where we considered videos that had appropriate resolutions, appropriate durations, appropriate content, and appropriate FPS. So from this, we sampled 150, or actually we didn't sample, we identified 155,000 videos that were within the within the characteristics that we had envisioned, which is similar in the sense how we did it for CONVID-1K, which you might remember Margaret also said was in some sense interesting for VQEG, but one of the problems with it was the qualities of the videos, which we also try to alleviate with this project here. So from these 155,000 videos, we altered them in such a way that we cut them down to 5 seconds. We took the middle part of each video. And additionally, what we did different to CONVID-1K was we didn't use Flickr's original encoding, so not the version that Flickr provided, but we accessed their API, obtained the originally uploaded video, and then re-encoded them by ourselves. On the right here, you can see a visual representation of the version that is supplied by just downloading the video from Flickr. The middle section is the originally uploaded videos, which were very big. We weren't able to store all of them for 455,000, so we re-encoded them such that we would have minimal visual impairments, while also being able to be annotated in a crowdsourcing session. And one of the points of this data set was that we wanted to emphasize diversity. So this would be diversity of quality and distortions, but also diversity of contents, contrary to some of the artificial data sets where you have only very few contents and then derive artificial variants of it. We really wanted to emphasize a large variety of contents. The dataset itself is split into two parts. We have the A variant and the B variant, which combined make up CONVID-150K, but they're sort of, due to the way that we annotated them, they are sort of separate, and they're also engineered in this way such that they're usable for some experiments that I'll be showing you later on. So they're split in such a way that CONVID-150Ka contains about 153,000 videos, and CONVID-150Kb is about roughly just below 1,600 videos. And the crucial difference here is the amount of annotations that we obtained for all of the different videos. The B part is annotated quite precisely with at least 89 ACR annotations per video, going up to something like 180. We only had limited control over the maximum amount of annotations due to the framework that we use, the crowdsourcing platform. But contrary to this, the A variant is annotated with 5 ACR annotations per video, so quite crudely compared to what's out there. But this is by design, and I'll show you why in a few slides. So as I said, the emphasis of this data set is on diversity, and I want to showcase a measure of diversity that we envisioned to specifically address the diversity of content here. So if you're familiar with Convert1K, one of the approaches we had was to ensure that we had sort of uniform sampling across a whole bunch of different quality dimensions. And here we didn't do any sampling. We essentially just chose all of the videos that we had that were within some characteristics, but we still wanted to check whether the sample that we chose was diverse in content. And what we did for this was we looked at the Euclidean distance in feature domain, and features here are the activations at the top level of an Inception ResNet v2. So essentially we fed all of the video frames through an Inception ResNet v2, looked at the activations at the last layer prior to the prediction, and then computed the Euclidean distance to other videos. And so just to sort of as a sanity check here, I want to show you what this looks like. So if this is one of the frames that we chose, I'm going to show you, if this is sort of the query, I'm going to show you out of the 155,000 videos that we have, the closest other video that we could find according to this Euclidean distance in feature space. So here you see the 3 closest videos. You see this. The first one is actually essentially a recording of the same scene just a couple of minutes later or before. But then the second and third video are also video recordings, in one case of a blue plane, like a toy plane in the sky. I think it's a toy plane. And the third one is a bird or a flock of birds actually also in front of the blue sky. So from this, in terms of a sanity check, this also makes sense already, that this is at least, it might work, right? But also, if you look at other examples here in the second row, you see a concert scene, which again, the second video is again a recording of the same concert, probably a different band. And the third and fourth video are also concert scenes with heads in the bottom of the part of the video, and then a scene in the background. And in the last row, you see underwater scenes with different kinds of animals. All these videos on the right are all the closest, second closest, and third closest. So according to the types of contents being depicted in the video, this is a rough sort of a rough sanity check whether this works. But it's not really a good way to measure content diversity in general, especially not when relating it to other data sets. So we wanted to come up with a measure that relates data sets between each other, which is what we call dataset coverage. So if you take a dataset X with items xi, then you can compute the distance of each of the individual items in X, so each of the individual video items, lowercase x, to another dataset, capital Y, by computing the distance to all of the videos in Y and taking the minimal distance, right? And so the minimal distance then tells you how far away do we have. So what is the closest distance in the other data set, closest cousin in the other data set we can find. And now we can choose a threshold, some threshold that we'll call S here, where by which we can define the coverage of dataset X by dataset Y, by computing the ratio of the numbers of videos where we find a cousin in the other data set that is closer than this threshold level that we chose, divided by the total numbers of videos in the data set that we're trying to cover. So this is a little convoluted, so maybe just a quick visualization of this that makes it very clear. Let's say we have data set X and Y in green and blue here, and this is the distribution of X in some 2D feature space. Of course, the feature space that we chose is higher dimension, but for visual purposes here. Now, if we consider S to be 0, so the distance that the cousin can be at is 0, and the coverage is 1. That means that all of the entries in Y are exactly overlapping with X. So essentially, X is a subset of Y, right? Now, conversely, if we choose S to be 1, so we allow a distance of 1, and the coverage is 0.8, so 80%. That means if we look at the distribution of Y relative to X, and we take, in this case, circles of radius 1, which is this, or radius S in this case 1, around all of the different cousins in Y, and we do this for all of the different entries in Y, then we would find that 20% of the videos are not within these concentric ball, not in these circles or in these spheres, and 80% would be. So this is our measure of coverage. And now by adjusting S, we can obtain essentially a cumulative distribution function, which tells us the comparison of essentially the distance that we have to go until we have a certain percentage of coverage achieved from X to Y, or from Y to X, depending on the order here. And this is what we did for a bunch of different data sets. So here, notice that we switch this around. So this is the distance. So this is the coverage of the data set given in the color scheme to the complementary. So all of the other data sets combined. So this would be in green. This would be the coverage of the other way around, the coverage of the complementary data sets, so COMVIT-1K, CVD, Qualcomm, and VQC by COMVIT-150K. And what we see here is that COMVIT-150K covers 50% of the other data sets with a threshold value of 2.25, whereas, for example, for Qualcomm, in order to cover 50% of the other data sets, we would have to increase this threshold level to 3.6. This is an indication that COMVIT-150K has better coverage of other video quality data sets out there, which is also in part, of course, due to the fact that it's much larger, but it's not solely explained by that, just due to the fact that also the contents being depicted here are more similar to what is also present in the other ones, but also contains contents that are not covered in the other data sets, which is, of course, a byproduct by having just more videos. So this is just a bit of showcasing the data set and its ability to be diverse. But then there's some considerations and the utility of this data set for visual quality assessment and training models on this data set. So when we think about, or when we as a group thought about what is our challenges for visual quality assessment, one of the things that always came up initially was, well, we had a lack of data, and this was one of the things that we wanted to approach with having this new data set. But if we actually look at the different data sets that are out there, then we can see in recent years, VQA data sets have really achieved quite large sizes, even compared to the largest IQA data sets in terms of total items or total ratings obtained. This is comparable, and IQA models are already quite eloquent. In comparison to aesthetics, to the aesthetics domain, which is also it's not technical quality, but some sort of variant of quality, right? We're still behind there, but with time, this will surely increase. But comparing the performance of VQA models to IQA models, we still see a large difference, which can't really be explained simply by saying that we're lacking content. So lack of content isn't really the central point, at least, I would say. The next point that you might say that we might come up with is that we have a lack of annotations. So if we look at this, then, well, arguably by judging by the total numbers of ratings, we're a little behind, for example, IQA here. And if we compare it to the numbers of ratings present in the aesthetics domain, there is a clear difference there for sure. But I would argue that not the annotations are the necessary problem. We can achieve annotations easily. The problem is more that we're running into the problem is slightly differently. So if we look at the total numbers of ratings or the annotations by the cost that we had, so if we normalize the cost with considering 3-second decision time in the case of videos plus the playback time, and considering $7.25 US as per hour, then we can see that the prices that we have that for video quality and image quality, technical image quality, compared to aesthetics quality is just ludicrous in comparison, right? We just don't have the same number, the same budget. So here we're talking about a budget, if you were to consider this normalized cost, of over $300,000 that you would have to spend to have the same numbers of annotations, right? And this is, of course, in an academic setting, not necessarily achievable. So the lack of annotations might not be the problem. It's more of a lack of budget, which is understandable considering, in our case at least, we're a university, right? We can't bring up a budget of this size. So the idea would be, if we have these numbers of annotations, and as we also saw, they're comparable to the IQA domain where the models are much stronger, maybe we just have to find a better way to distribute these annotations. But then there's also the point of having powerful models. This is also, of course, always a concern when you're trying to achieve high performance. Now, with the models that we also coupled with this data set, which are deep feature-based models, we actually achieved quite decent performance that seem to generalize well. And I just want to briefly state how these work. So again, we're working with deep neural networks. We're feeding video frames into Inception ResNet V2s. This could be any type of architecture that works in this sort of a modular approach. In our case, we worked with Inception ResNet V2 just due to its popularity. And then at every different module, we're performing global average pooling on the activations of each of the different kernels, and obtain a scalar value for each of the kernels at each of the different video frames, and concatenate them along the modules essentially, and obtain, in this case for Inception ResNet V2 and in our implementation, a roughly 17,000 dimensional vector. And now this we do for each of the different video frames. So we have one of these vectors for each video frame that we can potentially feed into a network. And this is also interesting for a variety of reasons. These features that are learned in these deep neural networks are also interesting to analyze. So the higher level features have been looked at quite a lot already, and OpenAI's microscope, for example, has also tried to visualize a whole bunch of these different individual neurons in these neural networks since we started work on this. So there's a lot more to look at now. But one of the interesting things as well is to look at how these features activate over the playback duration of a video. And this is an example of this. So what we see here is these are grouped by the different modules in the Inception ResNet V2 network. And then what we see here is for 3 sample videos shown in the different colors, you see the median level of activation over all of the frames during playback. And you can see that this changes drastically depending on what Inception module you look at. And we can also visualize different modules. So here, for example, this is the level of activation of different kernels in the stem. So at the very beginning of the network, you can see that these are more or less static levels of activation. They don't really change much. Whereas if you go to the upper end, so the last layer, this is usually related very much to high semantic content, so faces, animals, even cars. You see that this over the playback of a video changes drastically, which is to be expected because over the playback of a video, a person might enter and leave the frame, right? So these features are quite interesting, and we're looking to delve deeper into this. Now, given the feature vector that I explained to you, so we extract these features, and now the question is, how do we derive our predictions of this? We proposed 3 different models. This is the first one is what we call the FF, the feed-forward network. From the individual frame vectors, we compute an average feature vector, so we just average along the temporal domain essentially, and then feed this into a very simple structure of a network that's just fully connected layer with some activation, batch normalization, dropout, and then this with shrinking size leading into the prediction. Then we have a recurrent network, which makes use of the fact that we have these feature activations over the whole playback of the video. So this actually takes the whole feature vector at each time step as an input, and then this is fed through an LSTM network which then also feeds into, for technicality reasons, another layer there, and then predicts the MOS. And then we also have a hybrid network, which does both at the same time. So on the one hand, we have this this fully connected network that we have on the very left, and then on the right, we also use the LSTM network that makes use of all of the different individual frames, and then we concatenate the outputs of these and have a little header on top to predict the quality. The reason we chose this this third model is that we noticed that the models in the middle and on the left perform differently depending on what task we're working with. So we wanted to combine both and sort of get best of both worlds here. I'll just briefly show you the performance of this on the legacy data, so what we call the legacy data sets here, grouped by whether they are considered, at least according to our definition, as in the wild data sets or synthetic data sets. So the models that we envisioned here were, and the data set itself were targeted at improving prediction in the wild. And we can see here also that our feed-forward model performs well, specifically on these two models. Unfortunately, for the VQC model, not all of the other popular and high-performing models were evaluated, so it's hard to argue. And we're only slightly better than vBlinds, but nonetheless, we achieve peak performance here. And then in the case of the synthetic data sets, we're basically right behind the best performing model with our hybrid model. And you can see here very clearly that the difference in performance, that there is a difference in performance depending on what model is chosen. So for in the wild models, you see that the feed-forward model performs better, while for the synthetic models, for the synthetic data sets, the recurrent network performs better. Right, and then this is for the legacy data sets. Then we also, of course, have performance for our data set, for our proposed data set. Here we only evaluated vBlinds and TLVQM because these were the core methods that, first of all, were working very well on the legacy data sets, but also had easily executable code for over 150,000 videos. So some of the methods that we are aware of are very slow, and they would train for months and months before we would be able to obtain a result. So this is just a comparison to these two. Here we're comparing only on the small data set. So this is these are results only on the data set part that contains 1,600 videos. So trained, validated, and tested on 1,600 videos. And we can see here that the feed-forward model performs dramatically better than TLVQM, which, if we go back a slide again, right, TLVQM is the non-deep neural network best method by far, and also very recent. And in terms of synthetic models, actually, synthetic data sets, actually the best model to use in the first place. But we perform significantly better than it. What we also did was we did a sort of, well, it's not really weakly supervised learning, but what we did was we trained a model on not only the 1,600 videos with precise labels, but also included the 150,000 videos that only had this coarse 5 ACR rating annotation. And what we observed was that including this data, even though the MOS values are very coarse, right? They go in intervals of 0.2 scalar points, right? The model performance improved quite a bit from 0.83 to 0.86, and in the case of the hybrid model, more dramatically, even from 0.76 to 0.83, according to PLCC. So what we found here was that just using more data, even if the data isn't as precisely annotated, is useful. Now, one of the concerns of this is that we're extracting features first and then training second, right? So this is not classical transfer learning. So we wanted to see what the benefit, so and this has the benefit that the models that we're training itself, they're very small, and so we have high iteration speed, but we're not as flexible necessarily. So what we did was we compared the training speeds between sort of classical transfer learning and our approach, including our feature extraction time. So here in green, you see a completely unfrozen Inception ResNet v2 with a small header that's essentially retraining the whole network in two stages, each of 40 epochs. With first a high learning rate and then a low learning rate at the end. For concept, this would be completely unfrozen. In the orange case, this is sort of similar to concept, except that we are freezing the weights of the base network in the first stage and then unfreezing in the later to sort of avoid the large update steps that are done when you're adding these this header on top. In blue, you see sort of an alternate design where we don't just put the header on top of the network, but rather connect the header at each of the different global average pooling layers that we would have used in our extraction anyway. So essentially, it's hooking in at every different layer of the base network. And then again, we're freezing the weights in the first step and then unfreezing in the later step. And then finally, at the bottom, you see our model trained on the pre-extracted MLSP features. And you see here that the training time, so what you see is the training times. Training times are dramatically lower, right? So we're talking about 80 epochs in 37 seconds versus 45 minutes and more for the full transfer learning approaches, simply because the models are so much bigger. So this is one of the big upsides. Additionally, the validation SROCC is strictly outperforming the other models. So this gives us an indication that this is a good approach moving forward, especially if you're training multiple times, because each time you're doing the training in our case, you don't have to extract the features again, right? So all in all, the bottom line is that even if we include time for feature extraction for the entirety of all videos, we're still 36 times faster than training a completely transfer learning approach. So this takes away the idea that the models are necessarily not powerful enough. And we're going back to this issue, well, okay, so what about the budget? Maybe we can do something with our small budget to better improve the way that we can train our models, right? So I want to briefly touch on this as well, because these were very interesting findings, at least to our group and colleagues that we talked to about this. So what does the precision of the labels that we have on model performance at training time? So again, we have these two subsets of our data set, one that is coarsely annotated and one that's precisely annotated. In total, we're running up to roughly 1 million annotations. And what we did was we can say that, well, for the large data set, this can be sort of a low precision training set that gives you a rough idea of the types of contents present, the types of distortions present, and also a rough estimate of what the quality score would be. And on the precise data set, we can use this to perform validation and testing, but also training on a smaller scale. So we wanted to use a fixed budget, because this is usually what we were limited by, a fixed budget that we would have to distribute. And we would say that, okay, so we'll take 250 videos, each annotated with 100 ACR votes as a validation set, 250 videos with 100 ACR votes as a test set, all coming from this one part of the data set. And then we would consider 3 different training sets. One would be the remaining 1,000 videos of the small data set with 100 ACR votes as well. Then we would take 20,000 videos with 5 ACR votes and a third data set with 100,000 videos, each with 1 ACR vote. All these training sets have the same number of 100,000 annotations, an annotation budget of 100,000. So so if we were to have this knowledge prior to running the annotation procedure, we could say which one of these is better. So are we going to use more videos with less annotations or what? So the intuition that we had, so this is the graph that I'll show you briefly. So the x-axis is the numbers of votes used for the training MOS. So on the left, this means we have more videos with fewer votes used for the annotation, and on the right we have fewer videos with higher precision labels, so fewer videos and more annotations for each of the videos. And what we expected was that if we take a high vote budget, probably if the vote budget is high enough, then we could assume that going to this fewer videos is fine, because we would still, with a high vote budget, still be able to say that we have sufficient numbers of videos to generalize well in terms of content. But the interesting question was, well, what happens if we have a low budget? On the one hand, we're probably sure that if we have a low budget and then few videos, well, we're going to be only ending up with 2 videos, right? They're very highly, very precisely annotated, but 2 videos are never going to generalize well. But what happens if we go to this to the left side of this graph? Are we going to have a improvement here, or is the performance going to be worse? This was kind of what we were trying to find out. So what we did was we iterated over a whole bunch of different vote budgets distributed very similarly. Starting at 100,000 votes, this is what I showed you initially. So 1,000 with 100 votes up to 100,000 with 1 vote. So notice these are ACR votes, right? So in the case of the very right plot, these are in the case of the very left part of the plot, we're talking about 100,000 videos, each annotated either with a 1, 2, 3, 4, or 5, right? These are integer numbers, very coarsely annotated. And what we observed was that, well, actually, this performs better than just taking 1,000 videos with 100 votes, which we were actually surprised by. At least I was. My professor was not very surprised by it. He actually envisioned that this might be the case. And then as we reduced the budget, we noticed that this was a trend that was appearing. In general, it seemed to be that the higher precision on the labels didn't seem to be as important. At some point, this deteriorated. So with a vote budget of 2,500, we noticed that this starts to deteriorate. This is only 2,500 videos with 1 vote anymore versus 25 videos with 100 votes. And then as we go even lower, this deteriorates even further. But it's still better to just have 1 vote count mosses versus high precision mosses. But at some point, it starts to be more relevant to have sort of a middle ground, right? So having a middle ground between numbers of votes distributed on the training set, as well as numbers of videos present in the data set. And then finally, one last thing that we looked at was that we wanted to see, well, what happens if we also change the numbers of votes allocated to videos in the validation set? So what if the validation set has low precision labels? Can this generalize well even if the test set has high precision labels? So even if the test set has like the full range of values present. And what we noticed was that, so here, the x-axis is the numbers of votes comprising the training MOS, so changing the numbers of votes used for the training videos. And the different graphs here, the different plots here, are the numbers of votes comprising the validation MOS, so the numbers of votes used for the validation videos. And what we see here is, surprisingly to me at least, was that actually changing the numbers of videos for validation had very little impact. On the upper end, of course, distinguishing between 0.72 and 0.75 is an improvement worth considering, but still it's considerably less than I would have thought, considering that the test set was always made up of 50 vote mosses. So somehow models, despite having been only trained on integer MOS values and having been validated only on videos with integer MOS values, were able to obtain a 0.72 SROCC to videos that actually had floating point number MOS values, which to me is a large surprise. I completely did not expect that. So these are some of the findings that we had, and I know I already went way over time, but there were a lot of things that I wanted to chime in on that I had heard about in the last week that might find interest for some of you. And I would like to thank you and be welcome to answer any of your questions. Let me see if I can.
Thank you, Franz. Now, is there any content you had wanted to go over that you skipped because of perceived time constraints? Because if you want to go back and flesh out some area, that really would be fine. And I saw we briefly had a question from Lucian.
Yeah, so I think we'll go over questions there. I didn't necessarily skip over, I didn't skip over anything in the way that I wanted to talk about it. So I think that's fine. I'd be guided by the questions that we have. So let me see if I can find the chat. Oh yeah, thank you, Margaret.
Thank you very much for super interesting talk and very also detailed presentation. I found it very, very useful. So this is my just first comment. So far, as far as I understand, we can easily make subjective experiments with very few answers, and then still this is useful, much more useful than actually lots of answers per fewer videos. So I understand. Do you think that it would be valid to make this conclusion that actually what already said once Margaret is that actually the diverse in the video is much more important than anything else in making a correct video prediction, video quality prediction. So like this video part is really different. And then if this is so, then do you think this would be possible to extend this work to really identify like those videos, or like what is with the videos that makes prediction maybe not easier or harder, yeah, but maybe something like a different classes of videos that are scored specifically.
Yeah. So of course, I can't. So, with regards to your first question, I can't be sure about it. I didn't. I only have indications towards an answer of this question, and it seems to be that currently we are at a state where the contents being part of the contents in the dataset seem to be more relevant. That is assuming, so all of the datasets that we looked at had a distribution across the whole quality spectrum, right? Also in terms of scores, in terms of contents. So given that there are some sort of minimal steps that were taken, I would assume it seems to be, I would personally, my research will focus more on diversifying content, more so than being absolutely sure about super precise annotation. So this is sort of the takeaway that I took from this. But I don't have strong evidence that definitely shows this, right? But it's sort of the lesson that I learned from this. And so we looked into different ways that we could try to sort of figure out how we could improve this. So one of the things that we did was we tried to perform some sort of active sampling. So we tried to adaptively sample from these 150,000 videos a data sets such that the training would improve the quickest. So by adding more data to the training data set, we would improve on the test set the quickest, and then sort of go back and see what are the types of videos that we added, what are the types of distortions present there, what are the changes in the distribution of scores that we observe. But in these efforts, these are still in infancy, and we haven't really been able to sort of flesh out what it is there. But in terms of my research, this is where I'm headed and what I'm interested in going forward. Yeah.
Thank you. Thank you very much. And just one more question, because the networks that you used, they are not very complicated. So it seems that video quality estimation is much easier than detection, for example, yeah, which is reasonable, of course.
Well, that depends, considering the fact that in terms of the performance, we're still miles behind what other fields are doing, right? I mean, even if you compare just technical image quality to technical video quality, we're like I think on the most common data sets, we're now at like 0.96 SROCC or 0.95 SROCC, and we're scratching at the 0.85, right? So we're still well behind. These last percentages are hard to get. So it's and then in some sense you could say that so I see why you would say that it's easier, but on the other hand, you have to realize that the feature extraction that we're performing is building on top of these large data sets that were annotated using like object detection, right? Or sorry, object identification. So these networks already have imbued all of that knowledge. We're extracting it and then building on top of it. So I would not necessarily say that this shows that it's easier to do what we did. It's only easier if you know all of the stuff that you already know from object detection, right? Then it becomes easier, which makes sense because these models that we're using as feature extractors not only extract knowledge about where certain things are, but also at the lower levels, all kinds of different small Sobel filter-like features, right? So essentially, we have all of this knowledge condensed in these networks, and so if we were to train from scratch, I don't think we would achieve anywhere even near the performance that we have. So that would argue for the point that it's actually not easier. It's just that we're able to leverage more information.
Thank you very much.
Okay, I have a couple questions, Franz. Could you go back to the previous? Okay, so on this, the lines are a different number of votes for the validation MOS. The x-axis is the number of votes comprising the training MOS. What is the number of sequences?
So this is for the entire smaller data set. So this is all 1,600 videos. Sorry, so
Okay.
Training, validation, and test set is 1,600 videos. Validation set was 250 videos, and test set is also 250 videos.
Okay, so separate videos in training and testing in this
Yes.
comparison. Okay, so there's certainly a drop in the impact of the training MOS from 1 up to 50. If we look at your 14 to 26, 15 is BT500, 24 is P913. It looks to me like 4 or 5 votes is probably the sweet spot. Is that
Yes,
what your
so that's
dashed
also
line is?
so this is also why we have this dashed line there. So at around 5 votes, which is roughly a tenth of the budget of this graph here, right? We're essentially bridging 66% of the performance gap between the lower end of the performance with 1 vote and the higher end of performance with 50 vote. And so that's why also this was one of the motivations also to argue going forward, somewhere around 5 votes would be a good middle ground, and then just increasing the numbers of videos that you want to incorporate in your data set is what we would recommend going forward. And this is something that I will be using going forward as well, yeah. So we go from about 0.55 SROCC to 0.73, and at around 5 votes, we're at, what is it, 60, 66, 67, somewhere around there.
Okay, did you look at mixing different numbers of votes per stimuli? So part of the set has 1 vote, part of your training data set has 5, part has, say, 25.
So we didn't do it at the level of granularity that you describe. The only experiment where we did this was this one, where we are incorporating both parts of the highly precisely annotated data set and the whole set of Convert 150Ka. So right now, in this sort of adaptive sampling procedure that I described earlier, one could also go a level lower and just pull individual votes at the point where we're believing the most information gain back can be achieved. And then what we would end up would be a data set that has a variable annotation across the field. So we're investigating a whole bunch of different directions there, but I don't have any conclusive results for this at this point.
Okay, fair enough. And I know your data set is publicly available.
Yes.
And thank you for that. The metrics there, the 3 of them, I'm sorry, but could you remind me the difference between the FF, the RN, and the HYB versions?
Yes, so the FF is just a feed-forward network that is based on the average feature vector. So we're averaging the feature vector for all of the frames of a video, and we're just saying how active was this feature over the course of the entire video on average. Then the RN is the recurrent network, which takes all of the feature vectors over the entire video and are fed into an LSTM, so recurrent network, and then gives the prediction. So this should be able to leverage temporal changes in quality, right, or temporal changes in feature activations. And then the hybrid model is a combination of both. And ideally, this should be performing at the essentially of the maximum of the two, right? But in practice, it doesn't, and further investigation has to unravel why that is the case. Yeah, anyone who works with these models knows that they are a bit of a black box. So understanding exactly why things happen is a little complicated, yeah.
Okay, fair enough. Are these metrics available so other people could try them?
We have, so I believe, so I'm not sure whether all of the routines are available. The extracted features are available. So essentially the feature vectors are available to download, and the models are very simple to use. So anyone who uses deep learning should be able to just bunch these layers together. And I've already received a couple of emails of people asking how to help bug fix their implementations, and I'm happy to also collaborate if anyone wants to sort of recheck this. I'm happy if anyone rechecks my results as well. So so if anyone has trouble implementing these or would like to have these models run on some data, then then just message me and we can figure something out. The problem that we found ourselves with was that what we don't have available is the extraction methodology, so like a code for the extraction itself, because so this is always different depending on operating system, depending on video input and so on, right? So we don't have that publicly available. I'm still working on getting that online, and anyone who wants to evaluate our models on other data sets first has to extract these features, right? Because they run off of these features. So if you want to, get in touch with me and we can discuss this.
Okay, thank you. Are there any other questions before we move to the next topic? Okay, I just have one final question. The analysis that you presented here, is this in your paper that announced the CONVID 150K?
Yes, so this is all in there. There's more in there as well. It looks at the more detailed performance on legacy data sets and so on, and also some additional stuff is in there. So if you're interested in this, the paper is a great resource, I think.
Okay, could you add a link to your paper to the minutes?
Yes, I can do that. It'll probably be Monday when I do it, but I'll do it.
Okay, that's fine. Okay, well, thank you very much. Greatly
Thank you very much for
appreciate it.
having me. Thank you.
Okay, so at this point, we're going to change to the topic I mistakenly announced earlier. And let me open up that window. This is standard metadata. And in the chat, if you would like a quick overview of this topic because you weren't present on Tuesday, please let me know in the chat. Okay, I'm not seeing anything come up, so I'm going to presume that people who are here are familiar enough with the goals of the project that we can just dive into the content. So the first topic I thought would be interesting for us to delve into is the type of distortions that are of particular concern. And the current list as displayed here is compression artifacts, scaling artifacts, capture artifacts, in particular drawing attention to shakiness, blur, low light, and sensor noise. Production artifacts such as film grain noise, spatial and temporal aliasing, and frame rate changes. Geometric distortions resulting of incorrect fitting of the video sequence to the target's display. Packet loss, frame freeze, startup display, temporal discontinuities such as ABR resolution discontinuities, frame drops and resynchronization, and finally lip sync errors. What I'm interested in asking people present is if there's any other distortions that you think should be added to this list that we're drawing attention to.
Gunnar here, frame freezing, debuffering. For live content, I guess skipping is relevant, but maybe this is not valid for live content. I mean, or do you consider these the same? Because rebuffering, you don't miss any content, it just gets delayed, but with skipping, you miss actually content. So sometimes people judge this differently.
Okay,
I don't have a strong opinion. I just noted that it's not there.
Okay. Okay, that's a good thing to add. Is there anything else people think should be added to this list? I'm not hearing any other suggestions.
Margaret, this is Pablo.
Yes, please.
I don't have a specific suggestion. Only that just below the list you say that only we propose that the first 3 types of distortion can be considered in this scope. Since this list might vary, I suggest that you simply break it into 2 sublists: the one that you are considering, because they come before the transmission, and the other ones which don't. Because I mean, maybe production artifacts can be considered as well part of the. So I mean, simply if you treat them in 2 different ways, I would suggest making 2 different lists.
Okay, that's a good idea. Let me add a note saying that, but I've not actually added notes to Google Documents before. Can anyone point me to the right? Add comment, there we go. Okay, that's an excellent suggestion to make it into 2 different lists. Any other comments before we move on? Okay, hearing none. I remember there was, okay. So the areas where we were wanting guidance, one is which quality metrics should be included in the first version of the standard. This is not necessarily something we would need to decide since it could be a variable, but we at least want to have a list of known codes for metrics that we establish at the beginning, and which new subjective databases should be used for validation and statistical analysis of the existing and new metrics. And this is asking a different question than we did on Tuesday, where Tuesday we were focusing on no reference metrics, and here many of these will be full reference metrics that are being recorded. So are there any suggestions for databases other than the ones listed here that you would suggest we include as particularly valuable for validating metrics that would be mentioned here? The data sets we have currently listed is the Netflix for high quality TV, the recently released YouTube UGC dataset, the Facebook UGC dataset soon to be released. But what about for augmented reality, virtual reality, 360-degree video? Are there any suggestions from the immersive media group?
Hi, Margaret, this is Jesus. Yeah, we have the data set that we created for 360 videos for the test plan. I still have to send you the information to upload the contents and everything to the CDVL, but I think this should be done soon and you can use it.
Okay, so how should I describe this data set for?
This is, I mean, short 360-degree videos. And they are annotated with, yeah.
Okay, excellent. And any other suggestions for 360-degree augmented reality or virtual reality? Okay, not hearing any. For gaming content, we have 3 data sets that were mentioned on Tuesday as well. And are there any other data sets that anybody knows of for gaming that might supplement these? Okay, there are 2 live data sets proposed: live ETRI, which covers compression and spatial temporal scaling, and live VQA. Although it's older and lower resolution, there's more than 20 live data sets, and I'm personally not familiar enough with them to suggest which ones would be potentially better than those. And finally, the AVT VQDB UHD1 data set. I'm seeing no other comments, so we will move on. This table had our review of the data sets, and let me zoom in a little bit. Can you read the text for the data sets now?
Yes.
Okay. And are there any holes based on this description other than the data set that Jesus just mentioned that you are interested in filling? That is, don't suggest a data set, just a type of content. Okay. Okay, I'm not hearing a lot of feedback, and I'm thinking maybe people might be a little too tired to delve into the technical details of this segment. So the next topic I was considering looking at is the syntax. Could I have an indication on the chat if there are people out there who would like to right now delve into the syntax? We have a meeting set up in 1 month to look at this.
Looks like everyone is tired.
That's what I was thinking, Abhijit. Okay, I think we will leave it at this. And Cosmin?
I was just gonna say, I think it'd be good to wait for Johannes for that discussion anyway. So
Yeah. Yes, that was my inclination. Okay, I think we will close the discussion on this topic, and thank you for the data set suggestion. So let's look at the meeting minutes and approve those. Hold on a minute while I bring them up. Okay, day 5. I'm afraid the notes are pretty sparse today, so that will make it very quick to approve. For the most part, we just have the list of the presentations. And I think I might have gotten the order of these in IMG wrong. And
Yes,
Yeah, but,
maybe the second one
yeah. So
was, yeah. Go ahead.
Sorry. So Ashutosh was just after Alex. So basically, yeah, that's it.
Thank you. I thought I had that wrong. Okay. And we will note that a reference will be added here later. Is there any other information people would like added to this, to the minutes? Okay, hearing none. We will approve the minutes and consider the meeting to be closed. And thank you everyone for your participation and all of the interesting presentations.
Yeah, thank you all. I think it has been very successful meeting, very nice presentations, everyone. Also, I'd like to thank Femi for hosting the meeting and getting everything together in a nice way.
Thank you.
Thank you all. Bye.
Thank you, everyone.
Bye bye.
Have a good Christmas and New Year's, everyone.
Everyone, enjoy.
Have a
Bye
great
bye.
break.
Enjoy
Thank
the
you.
weekend.
Bye-bye.
Bye.
Thank you.